clusters. Next concept is burst to the cloud. Everyone heard of the concept? Yes, there. The boss doesn't know anything. Anyone got questions around that before I start? Let's just delete the GPU cluster.
How many people do you have locally currently?
Sorry, say it again.
How many people locally are currently bursting to the cloud?
I wouldn't know that, but it depends on what the application is. So I'm going to talk about high performance computing, and different people have different concepts of what bursting to the cloud means. Okay. So if you've got a single, let's just take all of these guys away as well. Maybe I must start with an analogy. High performance computing is pretty much like a rugby team, right? You've got a whole bunch of people all trying to work together for a single goal. If you don't have them as a single goal, you've got a losing team. So it's a team. You can think of them as the nodes. When you burst to the cloud and you leave half the team on one field and the other half on the other field, how do you get them to communicate? How do you get them to work as a single unit? So my concept is never have your team on different fields, always have them in one field. So bursting to the cloud, let's try this one. If you've got a local cluster, and say you've got 128 cores, your problem is actually just too big for that. The concept is, let's draw a cloud. The concept is, there's unlimited resources in the cloud. Push to the cloud. But what do you push to the cloud? Just, you get that to communicate with that. And this is where my rugby field analogy comes in. Having your team split means that becomes a problem, and you're actually back to a grid environment. So when you want to burst to the cloud, the better option is take that whole problem and push the whole problem there. You can have, say, 1024 cores, a bigger, better rugby team playing and doing the problem there. But to burst and to try and get just enough cores here, logically, you can do it, but performance-wise, it's just going to die.
The communication just slow it down so much.
Yeah.
Why would cost be the reason why you would split it up? Or is there...
Cost is one of the because I mean you're paying here, this is yours. But when it's too big, you need more. So performance-wise, it might actually just run faster if you just put everything there, and cheaper.
Yeah.
If you have a few cores here, that communication, it'll actually slow it all down. So it might turn out more expensive in the long run if you do something like that. Any other questions around that? So that's my philosophy, at least. In HPC environments, you take the whole problem and you move it.
How easy is it to use the infrastructure you've built out below the nodes and then be able to replicate that into the cloud environment?
How easy?
Because you want to progress as seamlessly from a local instance to a cloud instance as possible.
So the better way to answer that is how much experience you have.
Okay.
And the best, you need to have built these things to understand how they fit together. Your Lustre file systems. And if you have a look at Azure, you'll see that there is a Lustre file system. It's even Gluster and BGFS. Unless you've played with a parallel file system, you have no idea what you're doing here. And you might connect things very weirdly. So it's more about having that knowledge and then replicating it there. Because it is, you can replicate the entire logic. And you want them physically close together the same rack preferably,
Yeah.
because of that communication. So you can do HPC in the cloud, but you've got to be careful on how you set that up. Yeah.
So is the idea of bursts in the cloud that it's also an overflow facility that you know you've got on-demand processing and from time to time it will receive what your load.
I've got another sort of rule of thumb thing, and it all depends on your workflow. Engineers, us, we've got like a little workstation where we build problems and we test things. When the problem gets too big, we need to scale it up to something bigger. Let's call it a 128 core thing. And you find a problem, so you've got to iterate back, fix your problem, push again. And only finally, when you've got your model right, and it usually takes, so the fluid dynamics guys take about 6 months of this, and they've got approximately this as well, locally, to get the model right before they put to like thousands of cores. So they know the model is right, they iterate locally, and then once they know that's right, then they push to a cloud or HPC facility. And it should only be a once-off thing, cost-wise. If you're a heavy user of CPUs or compute, cloud actually never makes sense. And there's a nice sort of graph. We did this, you know, Alaris. Anyone else know Alaris and Tennis? So we did this exercise for them because they got a local compute thing, and they needed to know the numbers. When will it be paid off compared to cloud, and all those sort of things. So if you buy it, there's a once-off capex. Maintenance can be built into that, which is what we sort of do. Cloud is pay per use. So as you use, it accumulates. There's going to be a crossover point here. And when do you think that is?
What in years? Or money?
3
No,
months.
in time.
3 months.
Almost. For them it was 16 weeks, I think. They are a very heavy user, so in other words, they keep their machine busy, but that cost, if they translated that into CPU hours in a cloud environment, would have been just prohibitively expensive. Now they're not worried about that cost, and they're doing actual design exploration. They're just pushing things to the extent that they are now fighting and kicking, even though they've got a scheduler, and they're telling each other to get off the cluster so that they can use it. So it's a very interesting sort of study. Their cluster is a 36 core. The simulations aren't huge, but they've got many of them.